This is a section on just nuclear chemistry. There's a lot more nuclear chemistry that we actually covered in honors chemistry. However, the AP curriculum it's kind of peripheral, so we'll touch on it. We'll do a couple slides on it and do some practice and some review from other stuff. And there is a whole chapter in your book. They do a lot more in your book actually than is in AP chemistry. But you know, with the Fukushima plant that melted down, and obviously we live near TMI, nuclear chemistry is rather important to us. So you want to remember that everything is radioactive, and we know that the nucleus is made of protons and neutrons. And if you remember, that's what we call that, is that they're the nucleons. And remember, we have our atomic number that tells us how many protons we have, and then obviously that's our identity. And remember, like, one proton is hydrogen, two protons is helium, and you know, all that kind of stuff. Remember, every element has isotopes, and if you're an isotope, it just means that you have different number of neutrons, but you have the same number of protons. So remember, hydrogen has three isotopes. Being an isotope is completely normal. Just because you're an isotope doesn't mean that you are necessarily radioactive. And different isotopes have different natural abundances. So we have down here, we have 99.3% of uranium is uranium-238, and we have 0.7% is uranium-235, and only, astronomically small amount is uranium-234. So if you ever hear that people are being concerned that some country is enriching uranium, it's because they're trying to get more of the really radioactive uranium that can be used for nuclear power plants and or nuclear weapons. So when you dig up, different minerals, it's not like you're going to find sticks of uranium, and that's when what they talk about when you are enriching it. But it is enriching uranium is actually a really difficult process as well. All right, so here's just some little stuff that review from the last chapter. Remember, this is just in regards to electron configuration. So we were talking about why is explain why copper has the electron configuration. So remember, 4s1 and 3d10. Remember that filling a whole D level is more important than filling a small s level. So remember, the 4s is the highest energy level, and this is its valence electrons. And remember, it's very easy for an element to gain and lose its valence electrons. So what copper does, what silver does, what gold does, and then iron and some other things, they actually remove an electron from their highest s level and actually move it over to their D. Because if you have a half-filled D or a completely filled D, it actually lowers their potential energy. This is a big word you need to know. I know you've heard it from other lectures, but effective nuclear charge. Effective nuclear charge is how the electrons feel the nucleus, and the nucleus pulling in on it. So why does effective nuclear charge? Explain why atomic radius decreases as you go across a row. So remember, if you're in a row of the periodic table, you're in the same level, so you're in the same overall energy level. So what happens is, as you go across the periodic table, you're adding an electron to that same level, and what happens is that nucleus gets its effective nuclear charge increases as you go across the level. So what that means is that you're putting them relatively in the same spot, and actually it's like cinching your waist. It actually pulls it in slightly. It's not a significant, like a large difference, but it is slightly smaller as you go across. And then number 4 is, why is there such a large increase as you go down a family? And that's because you're going out shells. So like your first shell would be this one really close to the nucleus. Second shell would be here. Third shell would be here. So you're adding a whole new energy level. You're getting much farther away from the nucleus, and you're expecting a much larger change in atomic size. Whereas when you're going across the periodic table, you're in the same energy level. So it's actually a very minor change. Here's a couple things that you want to do. You want to put your elements in order from smallest to largest. So remember, your small guys are up and to the right. Your big guys are down and to the left. So if you find these guys on the periodic table, we're just going from up and to the right to down and to the left. Here we have the ionization energy. So first ionization energy just means we are removing the first valence electron. And for ionization energy, up and to the right is large and down and to the left is small. So if you're looking at your periodic table, germanium is the smallest, then sulfur, then carbon, then oxygen. And like it says here, sulfur and carbon are almost equal. So on a test, on the AP test, they probably wouldn't ask you that. Or they may ask you, like, why are they so close? Like, why would their ionization energies be similar? And then here we have the ions. Remember, when you're dealing with ions, you have to have this look at your protons and electrons, and you look for guys that are sticking out. So obviously magnesium is definitely smaller because his protons and electrons are just significantly less. But then we have our potassium ion, our calcium ion, and our titanium ion all have the same electrons. So then you have to remember about your protons pulling in. So since titanium has the most protons pulling in, it is the next smallest. Then calcium has the next most protons pulling in, so it's the next smallest. And actually potassium, with the least protons, is actually the biggest because of that effective nuclear charge that we discussed before. And then you probably just want to try this, but we want to write the condensed electron configuration for selenium. So that's just using our noble gas, and here's that. We want to know how many unpaired electrons are there. You can only have unpaired electrons if your levels aren't full. So our S is full, our D is full. The only place we can have unpaired electrons is in this 4p4 because that's the only level that's not filled. So if you draw it out, you can see that you have 2 electrons that aren't paired. If you have electrons that aren't paired, then you can be paramagnetic, and then you can be actually magnetic. How many valence electrons are there? Remember, valence electrons are in your highest energy level. So anything that's in our 4s would be our valence electrons. So we have 2 electrons in our 4s, and we have 4 electrons in our 4p, which means for letter B, we have 6 total ones. And then what's the most likely charge? Remember, you're either going to gain or lose electrons to have 8 valence electrons. Since it already has 6 electrons, the most likely thing it's going to do is it's going to gain 2 more, which would give it a -2 charge, and is what most commonly we see in selenium. All right, a couple more slides. All right, so different things, just getting back to radioactivity. Remember, you can look at the way they write things. Is a lot of times they'll actually have the name of the element and then its mass, so like carbon-14, carbon-12. You can also do your chemical symbols. So your mass goes on top here, your atomic number, your protons goes on the bottom. There's some common decays you have to worry about. You have alpha, which looks like a helium nuclei, so you can either write the alpha symbol or have good old helium. You can have beta particles, where it looks like high-speed electrons are coming out of the nucleus. Obviously, we know that there are not electrons in the nucleus. It looks like them, but it is not an actual electron. It's because neutrons and protons are actually made up of smaller things, and they can actually fall apart. So you can either write the 0, -1 beta or the 0, -1 E. And then gamma is just energy. And this is the stuff like why they put lead on you when you're getting x-rays and like you build bomb shelters and stuff. This is the most highly damaging. It can go straight through your skin. And remember, alpha is the least damaging. It can't even get under your skin. Beta, the people that are kind of paranoid, starts making sense because beta can be stopped by aluminum foil. So the people that wear aluminum foil hats may be onto something. And gamma is the one you need lead shielding, that kind of stuff. There's 2 types of nuclear reactions. You have decay, which is typically a natural occurrence. It's where you have something that's naturally radioactive falling apart into at least 2 or 3 things. Bombardment is what we do in particle accelerators. We take something that could be totally fine, we hit it with something else, it forms like a mutant middle ground, and then it'll decay. This creates really nasty things. This is what we do in nuclear reactors on a much larger scale in nuclear bombs, and this makes very high, like ridiculously radioactive waste. When you have natural decay, you actually make things more stable. When you have bombardment, you make things less stable. So here's a couple just examples from past AP things. It's telling you that mercury 201 underwent an electron capture. So remember, our mass goes on top. We look up mercury on the periodic table. His atomic number is 80. And we know that an electron has a mass of 0 and its charge is -1. So you always remember, add the top. 201 plus 0 equals 201. 80 plus a -1 equals 79. And you folks just made radioactive gold. So when we talk about alchemy and making gold, you can do it. It's just using nuclear reactions, and you make a highly unstable form of gold that is going to, or could potentially, kill you. In letter B here, we have a natural decay. We have thorium-231. They're telling us it's decaying to protactinium-231. So they're telling you what you're making. They're saying all it is decaying. So this is the only thing we have on the left. The 231 is our mass. Look up thorium. He's number 90. They're telling us we're making protactinium-231. Again, that's our mass. It's a 91. So then you're going to have to figure out what this guy is over here. And if you add up your things here, obviously our mass did not change, so this is a 0. Our atomic number actually increased by 1, so that means this has to be a -1, and we are beta decaying. And you're not necessarily required to know like what is beta, like what things have beta decay, what things have alpha decay. You just need to be able to figure it out if they give you the clues, so that you can see that. Here, oxygen 15 undergoes an alpha decay, very similar to C. And then down here, D is a bombardment one. So this is one where it's a little more complicated because you have more than 3 things. So we have aluminum. This is normal aluminum, like they could, you're like aluminum foil here. We hit it with a neutron. It makes this real nasty thing in the middle here that we don't even, it's an aluminum 28 atom. And they're telling us we get an alpha decay. So they're going to have to tell you everything but 1. So we get an alpha as a product, and then if you figure it out, we also get a nasty, nasty sodium. We'll talk more about kinetics when I get back, but the radioactive decay that we use for dating is always a first order. First order is always the same. The timing doesn't change, so if we're trying to use it to figure out how old something is, then it's good if it doesn't change. And when you have that characteristic thing, you have a half-life. And remember, it's just saying if I had 10 grams that was radioactive to start with, after a half-life, one half-life, I'll have 5 grams. After a second half-life, I'll have 2.5 grams. Third half-life, I'll have 1.25 grams, so on and so forth. Every isotope has its own one. Sometimes they're like less than a minute. Some of them are billions of years. Carbon-14's is 5,980 years. So again, it can be very short, very long, and there is nothing you can do to change radioactive decay. It doesn't matter if you're in the middle of the earth. It doesn't matter if you're in outer space. So this is the issue, because once you have something that's radioactive, there's nothing you can do than let it sit for its half-lives and let it eventually decay down to things that are no longer radioactive. The last couple of slides are just some real simple ones. So, you're welcome to go over it. This first one's just real simple. This is an old AP question. Sometimes they're real simple, sometimes they're tricky. But they said, okay, this is its half-life. It's 5.3 years. We want to know how much is left after 15.9 years. So this is actually an old multiple choice question. So if they're giving it to you in the multiple choice, it has to be pretty straightforward. So you can see here it's exactly 3 half-lives. So literally you're just dividing it by 2 3 times. So I started with 1 milligram. After 1 half-life, I'd have 0.5 milligrams. After 2 half-lives, I've had 0.25 milligrams. And after 3 half-lives, I only have the 0.125 milligrams. Again, this is in a multiple choice form, so it's going to be an easier one. Here, they kind of try and scare you because they say the isomerization of cyclopropane to propylene, blah, blah, blah. A couple of things that are important. First, it says it is a first order, which means that it is a dependable rate of decay. It says it has a half-life of 19 minutes. And it says, okay, we're starting at 1 atmosphere, and we're going to go down to 0.125. So they're saying about how long is that going to take. So we need to figure out how many half-lives that is. So again, I'm starting at 1 atmosphere. After 1 half-life, I'd be at 0.5. After 2 half-lives, I'd be at 0.25. and look, after 3 half-lives, we reach our magical thing. So what we're saying is it basically takes us 3 half-lives, and if each half-life is 19 minutes, 3 times 19 is closest to letter B. So these are the kind of questions you want on the AP tests, because they're super, comparatively, not difficult. And last one here, you want to fix this. I don't know why this was messed up in your notes, but the 245 for the curium should be on the top because that is its mass. It is not its atomic number. We do not have 245 elements. So they're saying that you really simply, we have the curium up here. And again, I don't know why these 245s, 248, 258 should be up. I don't know. I need to fix that. I apologize. But what it's supposed to be just showing you, if I would have had it correctly, is just a simple thing. You have curium, you're having a beta decay, and you need to figure out what you're making. And if everything was written correctly, you would see that it makes berkelium, which is named for Berkeley. So, hope this helps, and I hope you love nuclear reactions as much as I do. And I hope you're having a great day. So, enjoy your AP Chem.